and the few talks that I did get to hear were very interesting and indeed show all these non-trivial connections among this institute that I'm very proud to be part of. So I'm going to tell you today about some of the work that I'm leading here in Tel Aviv and trying to indeed make connections between it and things that are going on in and around Hiroshima. So I'll start, again, the core of my talk will be a more technical presentation of mechanical metamaterials, specifically combinatorial metamaterials that hopefully by the end of this hour, you'll know what I'm talking about, and maybe you'll realize some physical insights. But I want to give maybe a very, very brief introduction about where I'm from, and then I'll also at the end I would want to leave a few minutes for just mentioning a few other topics that we're working on in my group that are highly connected to all this. So just in terms of time management, so I should aim to stop at about 50 minutes after the hour, right? So did I get that right? Right. So I'll try maybe around 45 minutes, about 40 minutes from now. I'll maybe finish with my more specific technical presentation, and then I'll devote just a few minutes to quickly show you some other things, and then leave times for questions. Again, this remote Zoom setting is not optimal in terms of my interaction with you, but please feel free to interrupt me with questions throughout this presentation. I'd be very happy to discuss anything that will come up both during the talk and at the end. So as Ivan mentioned, I'm wait, let me see. Okay, good. So I am also the head of the Center for Physics and Chemistry of Living Systems at Tel Aviv University. Most of the work here is not directly related to topology, chirality, knots, etc. But still, I am coming from this soft matter and physics of living systems perspective. And much of my work is related to that, and we have here a center that brings together 30 research groups at Tel Aviv University, and we have both lots of internal interactions, and also we try to maintain also many international relations by bringing here visitors, organizing conferences, etc. I also belong to a smaller center for computational molecular material science. So these are essentially, this is a group of people that are doing all kinds of different types of numerical simulations, both development and application in various fields related somehow to material science and chemistry. The main thing that the center maintains is postdoc fellowships that we bring here people from all over the world to come and work and interact with people in the center. But what's much more exciting is the WPI at Hiroshima that I don't need to tell anyone who's here in the room about the center, but I will tell you about my perspective about how I see my work connecting to all this. And I found a famous quote by someone who happens to be in the room saying that 200 years ago, people worried about the limitations of horse-based transportation. And people were very worried about all the ways that horses walking and pulling carriages through the cities would cause. And then that problem suddenly became irrelevant because automobiles appeared, and that's something that people didn't even think would appear, both technologically and also at the society level, in terms of just replacing how things were done before that. And I think I can join Ivan's vision in saying that metamaterials that we, not necessarily I, but humanity is designing and developing, could just have physical behavior that is some things that we didn't imagine before, and that these would, completely change the way that, many things in our lives work, and that would eventually lead to a substantial reduction in energy, both in construction and also in maintaining many engineering systems that require lots of energy today. So I'll tell you about not just metamaterials, but specifically combinatorial metamaterials, and I'll try to explain what I mean by that. I'll demonstrate some insights that we already reached about chirality, topology, knots, etc., that are very important in these systems, and I'll show you maybe just some first steps in how we understand how all these mathematical structures affect the functionality, in this case, the mechanical response of these metamaterials. And this, again, following the spirit that I tried to convey a moment ago, will hopefully indeed contribute to our ability to, as a society, to function in a more sustainable manner. So, before getting to telling you what are combinatorial metamaterials, I must not forget acknowledging all the people that contributed to this work. A lot of people in my group, and all this started for me and still is going on with a very warm collaboration with my colleagues in the Netherlands, mainly Martin van Hecke and his students and postdocs, and now Corentin Coulet also has his very impressive group in Amsterdam, and I continue to collaborate with all that gang. At Tel Aviv University, Yoav Lachini has an interesting lab for all kinds of mechanical phenomena and complex systems. And some of what I'll show you is in collaboration with him. On the theoretical side, I also collaborate with Cristiano Nisoli from Los Alamos National Lab in the US, mainly about connections between mechanical systems and magnetic systems. And during the last year, thanks to the Institute in Hiroshima, I started collaborating about all of these things with Tamas Kalman, who just visited Hiroshima and is now back in Tokyo, and all this certainly is going in directions in which I see lots of further collaboration with him on the more mathematical side. What are combinatorial mechanical metamaterials? So I'll try to explain that through an example. So consider the triangular lattice in 2 dimensions. Okay, so this is just what you're seeing here in the bottom. Wait, let me. Okay, so this is a small portion out of the very big triangular lattice, and now let's try to build this triangular lattice mechanically out of, say, macroscopic sticks connected with magnets. And now I want to build this triangular lattice in a very specific way, which I'll try to explain in a moment. But let's say that each such black triangle in my lattice is made out of 6 red sticks that form a big triangle. And inside, I'm going to add these 2 green sticks. Okay, so in a moment, I'll explain what is the mechanical behavior of this structure. But first thing that should be obvious to you, maybe from the more mathematical or side, is that this object, okay, this red triangle with the 2 green bars inside, is anisotropic, right? If I'll rotate it by 60 degrees, I'll get a triangle sorry, if I rotate by 120 degrees, I'll get the same red triangle, but with the green bars positioned in a different way. So overall, there are three possibilities of how would I orient this triangle in the lattice. Okay, so that's just one thing to note, and we'll get to that in a moment. But now let's try to understand the mechanical behavior of this structure. This structure has what we call a floppy mode or a zero energy mode. Okay, so generally physical systems, if they deform, if the atoms comprising them or the macroscopic bodies comprising them move around, the energy could change, and we can talk about the stiffness of the structure in terms of how does that energy increase as you deform it. But this structure that I'm showing you here has a way to deform which doesn't cost any energy. Okay, so you can think of these sticks as chemical bonds. A chemical bond is something that, again, from my physics point of view, a chemical bond means that as you change the distance between these, between two objects, the energy changes. There's some reference distance that you want to have, and if you change that a bit, the energy will rise. You're at some local minimum of the energy. So here I can think of these sticks as mechanical bonds, but these mechanical bonds are very, very stiff. If I want to compress or stretch such a plastic stick, I need to invest a very strong force for that. It's not something that I can do with my fingers, but in principle, I can think of that, and I can also think of maybe actual mechanical systems in which these sticks are not these huge plastic pieces, but rather some springs or some rubber that indeed I, with my fingers, can deform. But still, what you're seeing here below is a way to deform this structure without changing the length of any of these bars, and therefore without any energetic cost. Okay, so this is what we call the zero energy mode or floppy mode of deformation. But now, getting back to the anisotropy of this building block, I can position each time I repeat this building block in the lattice, I can position it in one out of the three possible orientations, and I'm denoting that by red, green, and blue, just for visual assistance here. And as you can see, I can now build my lattice such that each building block will be oriented in a different direction. And now I can ask, what is the mechanical response of this structure? Okay, so this combinatorial metamaterial, there's a huge number of possibilities of how to build this metamaterial. Okay, and I want to consider this huge class of possible metamaterials that I can build out of these building blocks just by these discrete degrees of freedom of what's the orientation of each block within the lattice. So in order to understand whether this structure is mechanically floppy or flexible rather than rigid, what we need to do is to consider a loop within the lattice. I need to start at some point. Okay, so if I have an isolated triangle, I can deform it as shown here in the left. But now, when these triangles are connected together, they somehow need to deform in harmony. So I'm going to consider one triangle, perform some path throughout my system until I return to the triangle I started from, and I want to see whether I can deform all of the triangles along that path self-consistently. Okay, and in that way, I'll test whether this entire structure has a floppy or a zero energy mode of deformation. Okay, so now the shortest path I can consider is just taking 6 triangles connected in such a hexagon around the vertex in the lattice, and I'm showing you here just 2 representative configurations. I could have chosen any one of the 3 to the 6th possible orientations of these 6 triangles, and I'm going to test whether I can now deform each one of these triangles according to the mode I showed you before, to the floppy mode I showed you before. Turns out that this configuration here on the left, I can simultaneously deform all of these triangles, so therefore this is mechanically compatible. It has a floppy mode, whereas this structure here on the right, if I'll try to assign the directions of displacement, I'll get some contradiction here. So here in the top, you see these 2 points that want to move towards each other, but there's a bar between them, and I wanted to keep the distance between two such points fixed. If I move these 2 points 1/3 of each other, I'll need to shorten this bar. So there's some mechanical frustration here, and therefore this is rigid. And you can also see this experimentally here. So maybe in this video you cannot sense what force did my collaborator have to apply here in order to deform these structures. But what you can observe geometrically is that in this structure here on the left, okay, which is just a 3D printing of this schematic drawing I'm showing here above it, all the deformation is by changing the angles at the contacts. All of the bars stay straight. Whereas in this structure here, which is frustrated and therefore stiffer, you can see that some of these yellow bars are bent, okay? The fact that it's bent, okay, even though with our naked eyes, it's hard to identify what's the distance between the ends of each such bar. That's something that we can do just with, computer analysis of these images, but with your bare eyes, you can recognize that some of these bars are bent. When a bar is bent, this means that the end-to-end distance has been shortened, okay? So this means that the deformation here is not only by changing the angles, but also by changing the length, the end-to-end length of some of these bars. And that's why these structures are stiffer. Questions so far? Yes? Is there a question or? Okay.
Yes.
Yes.
Okay. So I wonder, in 3D, is it are there like a lot more, because it can move in many more ways? Are there a lot more?
Again, in 3D?
Yeah, 3D, are there a lot more like globally floppy modes because it can move in?
Okay, I'm not sure I heard you well. You're asking about 3 dimensions or? Maybe you could move closer to the microphone because I
Maybe it's in the more. Can you hear me better now?
Yes, thanks.
So I was asking, in 3D, is there a lot more like configurations where it will form globally floppy modes because it can like move in that additional direction?
Okay, so there are. Okay, the answer is that yes, things could be more complicated. It does not necessarily have to do whether it's 2-dimensional or 3-dimensional. So I'll soon show you also a 3-dimensional example, which actually is more or less at the same level of complexity of what I'm showing you here. There are, and we are considering also 3-dimensional structures, and obviously, all this theme of topology and knots, etc., is relevant in 3 dimensions and not that much in 2 dimensions. There are several aspects to what you were asking. So one issue indeed has to do with dimensionality, and I'll get to that shortly. Another issue has to do with how many floppy modes of deformation each block has. So here I've chosen a relatively simple structure that has only one floppy mode of deformation. I could also build a unit cell or a building block. Again, excuse the quality of my drawing. I can also build a building block that looks like that. Okay, and then this thing, since I removed one bar, I removed one constraint, so I have an additional degree of freedom or an additional floppy or zero energy mode. So I can now wait. Okay, so I have one mode of deformation that looks like that, and another mode of deformation that looks like that. Okay, so even in 2 dimensions, I can say, in this case, just remove a bond. Now I have a different building block. This building block has 2 floppy modes, and now I can ask all kinds of combinatorial questions about what happens if I now build a lattice made out of these structures. And we've done some things along these lines that maybe I'll get to briefly mention that later. So in this sense, we can do that even in 2 dimensions. And in 3 dimensions, I think what the exciting things that are happening is that you can have all kinds of topologically non-trivial structures, and which I'll briefly show towards the end of my presentation. So I hope that was helpful for that question. Okay, so let me move on. And as I said, please stop me if there are further questions. But just getting back to this difference between the compatible and the frustrated structure, I want to explain what is the reason that this specific configuration here on the left is mechanically compatible, the one on the right is mechanically frustrated. The reason for that is that we want to have alternating directions of displacement, and I'll denote these alternating directions of displacement by these blue and red dots. Okay, so no, sorry, I want to do the other way around. Right, so if you look at the experimental image at the bottom, if I draw these arrows, you can see that they alternate in terms of going in and out of the triangles. Since you want to return to what you started from, you need to have an even number of such flips. Whereas if you have a configuration like the one shown here on the right, in which you have an odd number of such flips, you cannot do that. Okay, so the fundamental reason for being compatible versus frustrated is whether these minimal loops are even or odd. Okay, so now if we look at an entire lattice, I can now look at all these triangular building blocks in the lattice. Each one of them has 3 points at which I'll define some binary variable, which for historical reasons, I'll call it the spin. Has nothing to do with spinning around, has nothing to do with magnetism. If some people have that connotation when they hear the word spin, it's just a binary variable, which can be plus or minus 1. And my rule for mechanical compatibility is that in each such triangle, I want that these 3 spins will not be all in or all out. The mathematical meaning of this condition is that these 3 numbers, sigma 1, sigma 2, and sigma 3, which each one of them is plus or minus 1, I do not want all of them to be plus 1. That would give their sum would be plus 3. And I don't want all of them to be minus 1. Then their sum would be minus 3. I want their sum to be plus or minus 1, right? I want to have 2 ins and an out, or 2 outs and an in, and that would give me a sum which is plus or minus 1. So now I can write a mathematical model which essentially just sums over all of these triangles, and in each triangle just takes the values of these 3 variables, sigma 1, sigma 2, and sigma 3, and squares that, and searches for a minimum of that, right? I want that everywhere, each one of these terms of sigma 1 plus sigma 2 plus sigma 3 squared would be 9 rather than 1. Okay, I want to have plus minus 3 instead of plus minus 1. Just, mathematically, the simplest thing is to square that, and then you want to get 1, which is the lower value, rather than 9, which is the higher value. And that maps to you know, the type of models that we study in statistical physics or condensed matter physics, in which we write some object, which we call a Hamiltonian, which is the energy function of the system, and we say try to minimize that. So just by opening the square, you can map this to what we refer to as a two-body interaction, a model in which you just sum over all the pairs of neighboring points along this lattice. But now the lattice is not the triangular lattice, but rather it's dual, which is the Kagome lattice, which you see by all these purple triangles. And this model has been analyzed long ago and fully solved. So we know how to describe the behavior of this model of binary spin variables that prefer to have opposite values, or anti-parallel or anti-ferromagnetic, as we call that in magnetism, on this Kagome lattice. And the specific property that I want to take out of that solution is the fact that if you try to minimize the energy, which is what we get in statistical physics at zero temperature, there are many, many different ways to do that. How many? A number that grows exponentially with system size. Okay, so if n is the number of points in this lattice, the multiplicity, the number of possible ways to arrange these binary spin variables such that you satisfy this condition, is equal to the exponent of some number that can be exactly calculated times the number of nodes, which means that as your lattice size grows, the number of possibilities grows exponentially with the size of the lattice. Okay, and here I'm showing you just one representative such configuration. Because this number grows exponentially with system size, most of these configurations are non-periodic. Okay, so even though I have lattice-based systems, the values of these spin variables, these red and blue dots here, which represent the direction of the diffraction, seems disordered. Okay, so it's not disordered. There's some hidden order here, but it's certainly, and most of them are certainly non-periodic. Okay, now show you how I can use that in order to build a mechanical metamaterial with a global floppy mode. So now I'm going to take such a ground state of that spin model and orient each triangle such that it would be consistent with this deformation, which is equivalent to removing all the frustrated bonds. Wherever I had a bond between two points that are of the same color, I'll just remove it. Okay, so this would determine the orientation of my blocks. And now I'll just draw again this triangular framework, and I get now a mechanical metamaterial, which, again, if you wouldn't see this derivation that I just showed you, you would say, oh, this is completely disordered and random, but it was constructed such that it would have a global floppy mode, and you can see an experimental demonstration of this here. So here you see a lattice, which again seems at first sight to be disordered, but actually it was designed in a specific way such that all the deformation would be just changing the angles at the corners without changing the length of any of the bonds. Questions? Okay, so one of the properties of such a compatible metamaterial, and metamaterial that was constructed such that it would have a global floppy mode, is that all of the loops in it have an even length. Okay, so although this structure seems disordered and non-periodic, there's a specific property, which is that all of these loops, and I'm now looking only at the purple bonds, I'm ignoring these black bond would just form a boring triangular lattice. The interesting part is in the purple bonds, and they form all kinds of different loops, but they all must have an even perimeter. Okay, so now I have some understanding of the compatible structures here. Now let's try to understand how can we make such a metamaterial incompatible or frustrated. So first, and this will lead us to more topological behavior in these lattices. But now, first I want you to note that if each minimal loop is even, also any bigger loop that I'll draw in the lattice, because it's made out of many even loops, this big loop would also be even. Okay? So now I'm going to start with such a compatible metamaterial and try to perturb it. Perturb it by rotating one triangle. So here I took this configuration shown on the left and I rotated this triangle highlighted here in yellow. If I rotate it, I cause two loops to change their parity, okay, right? To increase or decrease their perimeter by one, and that changes them from even to odd. But if I look far away from this defect, this big blue loop around it stays even. It's not affected from the fact that there's some defect here. So I do not expect to see a long-range mechanical effect of this defect. But now, if I continue rotating triangles all the way to the ground of the system, I'll be left with a single odd loop, and all the other loops around it are even. This means that if I'll go around some big loop far away from the defect, and again, here I'm just so that we can see this on the screen, I'm showing you a small system, but we can consider a much bigger system in which I'm considering a big loop that goes far away from where the defect is positioned. I will identify that there is some topological charge somewhere within this region. Okay, so this defect has a topological signature, and I expect to find also some long-range mechanical consequence of having that defect here. Okay, so let's try to see how can we demonstrate such long-range mechanical consequences of having a topological defect. So for that, I'm going to consider two different designs. So here on the left, I'm showing you actually two copies of the same system without a defect. And here on the right, I'm showing you two copies of the same system with a defect. Where's the defect? The defect is in this region in the middle that I cut out. Okay, so you can think of this as if there was some singularity there, and I just removed the region with the singularity from my material. So now my material is in the shape of such a ring. And in one case, which is what's shown here on the left, there wasn't any singularity in the region that I cut in the middle. And in the second case, shown here on the right, there was a singularity, a topological defect in the middle, and I cut that out. But the structure knows that whether there is or isn't a singularity or a topological defect there in the middle, even if that middle or that core is removed. Okay? So how do we see that? What we're now going to do experimentally is to take two triangles that are highlighted here in yellow and just pinch them, okay? Just mechanically deform them, okay? So the two triangles shown in yellow, here, we're going to just impose these two green deformations here. We're just going to pull that triangle and force it to deform according to its floppy mode if it was isolated. But it's not isolated. It's part of this big lattice, so it has to somehow deform and cause all the rest of the material around it to also deform in a consistent manner. If there's no defect, this means that any loop in the lattice has an even perimeter. So this means that the distance between the two triangles I picked could either be even both when I go above the hole in the middle and even as I go below the hole in the middle, or if I take slightly different triangles. Okay, so now the difference between this drawing here and this drawing here is that I'm now actuating a slightly different triangle, just a neighboring triangle. By actuating this triangle shown here on the right instead of this triangle shown on the first image on the left, I'm now causing the total perimeter of this loop, which is even, to be made, instead of being made out of two even parts, it's going to be made out of two odd parts. So here, both as I go under the center of the system and as I go above the center of the system, the length of my path is going to be odd. Whereas if I have a topological defect in the middle, as I said before, I don't need to have material there. I can cut that out. There's some topological information that is that the system knows, even if you cut out that core region. Now, the total perimeter is odd. This means that you need to have a sum of an even number and an odd number above and below. And depending on which triangle you actuate here, you can cause the even part to be in the top or at the bottom, and then the odd part would be in the other side. Okay? So now let's understand what do we expect just from a very simple mechanical calculation, which just treats all of these black lines as simple springs. Okay, just a spring that has a linear response, namely that the force that it applies is proportional to the extension or compression of that spring. In this case, if I do the first experiment here on the left, which is taking a structure without a defect and actuating two triangles that have even distances between them, I'll just actuate the global floppy mode of the system. Okay, so this system has a global floppy mode. If I force these two triangles to deform, I'm going to force all of the other triangles to deform, and I'm marking here by black arrows the displacement, and I'm coloring the bonds in blue or in red according to the stress on them, whether they're stretched or compressed. If they stay relaxed, I draw that in white. So here in the first drawing on the left, all of the bonds stay white. You don't see them, and you see lots of black arrows, all of the same magnitude. This means that there's a global floppy mode here. There's lots of motion without any stretch, without any stress, without any stretching or compression of the individual bonds. Here, if I take this other pair in which I have odd distances both above and below, now, as you can see, you get lots of stress both above and below because there's some incompatibility or trying to cause a deformation along an odd path. If you have a topological defect, then you can see that by switching which triangle you actuate here, you can cause stress to be concentrated either in the top part or in the bottom part, wherever you have an odd distance. And then when you have an even distance, you'll have lots of deformations, displacements without that much stretching or compressing of the bonds. So here above and below, you see lots of black arrows, which means you have displacement, but you hardly see colored bonds because all the bonds are very close to white, which is undeformed. Okay, and the other side, you hardly see black arrows, namely much smaller displacement, but you do see lots of blue and red colors, which represent stretched or compressed springs. Okay, so this is the theoretical prediction based on this, just a simple model in which we say, okay, each one of these bonds is an elastic spring. So now we went and did this experimentally. Experiments are relatively easy. Again, as a theoretician, it's very easy for me to say that an experiment is easy, but I think that these experiments are, do not require super fancy experimental facilities. You just 3D print the network that you design on the computer, and then in order to actuate and cause this extension of two specific triangles, you just insert a much more rigid plastic bar here, which is longer than the relaxed distance between these two points. And then you put a white dot of ink at every vertex of this lattice, and you take an image, and from the displacements of these white dots, you identify all the deformation in the material, and from that, you can also calculate the stress on each one of the bonds. So the experiments don't look exactly like this very simple theoretical model. Things are a bit more messy. Here you do see some stress, but certainly when you have a topological defect, you can see that in the first case, you have stress that concentrates more in the top part, and in the second case, you have stress which concentrates more in the bottom part. Again, I won't get into all the mechanical details here, but I'll just tell you that we theoretically understand where this comes from. This comes from the fact that the hinges, the contacts between these different bonds are not perfect. Namely, you cannot have a completely free motion there. There is some resistance, some mechanical rigidity at these hinges. And when we put that into the model, we do get much better agreement with the experiment. Questions? Okay, so we can do the same thing in all kinds of other lattices. I'll quickly show you some things we did for the honeycomb lattice. So here we have some different, in this case, hexagonal unit that is designed in some way which looks here complicated, but I can easily explain why we took this specific design. But in terms of its behavior, as you can see, it has one floppy mode, and this floppy mode has this behavior that you can see here on the right. And as you can see, even though the geometry of the actual structure isn't very symmetric, the floppy mode is pretty clear and symmetric, and you can just draw this red line that indicates the orientation of this hexagon. And now if you have a big honeycomb lattice, you can orient each hexagon in a different direction, and that may look a bit similar to a nematic director field that we know from liquid crystals. And the interesting thing is that if you want to understand the mechanical defects of this structure, they are somehow related to topological defects in that nematic director field. So here, similarly to what we did in the previous lattice, I'm going to consider a minimal loop in the lattice. Here, the minimal loop is just 3 hexagons meeting at a vertex, and you can verify that there are only 4 possibilities of how to orient these 3 hexagons meeting around the vertex, again, up to rotations and inversions. And these 2 cases on the left are mechanically compatible, and these 2 configurations on the right are mechanically rigid. And it's interesting to note that these mechanical defects are related to either terminations of such a nematic director line or to branching of such a nematic director line. And again, I won't get too much into that right now. I just want to quickly show you another mechanical consequence of that, of having defects. So here, this is this honeycomb lattice with a topological defect in the middle, and I'm showing you here 2 copies of the exact same system, and I'm just pressing on it in 2 different ways, on the left and on the right. In one way, I press in a way such that I'll have an odd path above and an even path below, and then I get lots of stress above and not that much stress below. And in the other case, I'm just flipping, as you can see, I'm flipping the direction of the of the texture that I'm pressing with here on the right boundary, and that just flips the parity and causes the oddness to be on the bottom side of the defect and the even behavior to be on the top side, and that causes stress, which is represented here by this color code in which I paint each hexagon to concentrate below the defect rather than above the defect. Similarly, if I have 2 defects, I can cause that oddness or concentration of stress to be either in the region between the 2 defects or in the region around it. Now, why am I excited about the second part? Because that's where I can now generalize that to 3 dimensions. Okay, so I'll very quickly show you, and again, without complete explanations, due to time limit, I'll briefly show you how we can construct a 3-dimensional mechanical metamaterial, combinatorial metamaterial, and then how we can use defects in that metamaterial to steer stress in more topologically non-trivial ways when we are in 3D rather than 2D. Okay, so now this is going to be our building block. Now it's going to be a cube out of a cubic lattice in 3 dimensions, and we're going to choose this specific design just because it has a relatively simple anisotropic floppy mode. And now we're going to build a lattice out of these blocks. Each one of them can be one out of 3 possible orientations: red, green, blue. And similarly to what I showed you before and explained in detail for the triangular lattice, also here parity is what's responsible for compatibility. If I the direction of the deformation returns to what I started from, I'm mechanically compatible. And if it doesn't, I have a mechanical defect here. But now my mechanical defect is this entire edge in my three-dimensional lattice. So now instead of having a point defect, I'm going to have an edge defect or a line defect. These defects cannot terminate in the bulk, and they can form topologically non-trivial structures. Is there a question there in the back? I'm not sure I can see properly, but no? Okay. So, and this actually has to do with the question that I was asked before about whether in 3 dimensions you can get more possibilities. And here we also ask the same, the same question of how many different ways are there to orient the different blocks and still get something which is mechanically compatible. And it turns out that here, that number grows exponentially, but not with the number of blocks, but rather with the surface area. Okay, so if I have a lattice of L by L by L, it has L cubed cubes in it, but it turns out that the multiplicity of compatible structures grows exponentially only with L squared and not with L cubed. So it grows exponentially with the surface, which is what we call subextensive in statistical mechanics. But still, we can use this to design a metamaterial that would deform to any structure we want on its surface. So this is an experimental example of a 10 by 10 by 10 such a lattice, which we designed such that when we press on it, it would deform to a specific pattern that you briefly saw it in a moment, and soon you'll see it more nicely and more clearly. Okay, so in one direction you just get this checkerboard, but if you rotate it properly, you can get anything you want, including this thing that you see now. Okay, but now back to defects, topological defects, and their mechanical consequences. So if we now generalize what I showed you for the honeycomb lattice, now going to this three-dimensional simple cubic lattice, as I said before, the defects would be edges within this lattice, and now I'm showing you a top view of such a minimal loop of 2 by 2 by 1 blocks, and the edge here at the center that's coming out of the screen can be either compatible, as we see in these cases, or it could be defected or frustrated, as in these two structures here on the right. So now I can build a big lattice in which I have such a line of defects, or a defect line. Due to topological reasons, it cannot terminate in the bulk. It has either to terminate at the boundary of the system or to close a loop. So here I'm showing you a line defect. It's just this dark green line here. And now I'm pressing on it on the system from two sides. And similarly to what we saw in 2 dimensions, if you look just at this 2-dimensional XZ slice here, you can think of this as analog to what we saw before in the honeycomb lattice. There is a point defect here, and you can cause stress to be concentrated on one of its sides, and you could equally make the stress concentrate on the other side. But now in 3D, you can also cause this stress field to twist as you go around the defect line. So that's one thing which exists in 3 dimensions that doesn't exist in 2 dimensions. Another thing you can do is take this defect line, and instead of having it terminate at the boundaries, you can have it close a loop. So this is a loop in the lattice, and this, you can think of this as some 3-dimensional extension of having 2 point defects that I showed you before in the honeycomb lattice. And now you can cause stress to be between these defects or within this loop, as you see here on the left, or to avoid that region, and all the stress would concentrate around it. Very recently, we started looking together with Tamash Kalman about at possible topological, more interesting and exciting topological structures that you can form out of these defect lines. And we now know how to form any knotted structure you want of these defect lines. So here I'm showing you just in blue the defect lines within the system. And I'm not drawing all of the blocks that are building this metamaterial. Each one of them is oriented in a different way, in a very sophisticated way that we designed such that we would have the defect lines form these topologically non-trivial examples. So I think my time is almost up. I'll just very briefly reminded you that what I try to present and explain here is all this notion of combinatorial mechanical metamaterials. Metamaterials, these are structures made out of some repeating building blocks that are macroscopic, and that the essential physical response in them has to do with mechanics. And the combinatorial aspect is the fact that we take anisotropic building blocks, and then we can orient each such block in the lattice in a different orientation, and by that get a huge number of possible structures. And the important thing, also relating maybe to the more discrete math side of me and of this center and the people here in the audience, is that the physical behavior is very strongly dominated by the combinatorics of the mutual discrete orientations of these building blocks. And there's lots of interesting mathematical questions that arise here that, we're also trying to solve them for the mathematical interest, and also trying to identify connections to actual physical and consequences and applications. So finally, I want to very quickly tell you about all kinds of other things going on in my group that are highly related. So we're also looking at not only geometry, but also memory and in the dynamical response of mechanical metamaterials. We're also looking at colloidal systems that I treat them also, at least the systems I'm looking at, I'm treating them also in a sense as some sort of a metamaterial. So we have micron-sized essentially plastic particles suspended in water. So you can think of these as some macroscopic atoms that move around, but you have not, because they're so large, again, a micron is huge compared to the atomic length scale, you can see them under the microscope, as you can see here. So these are experimental images here, this one and this one, two setups, but you can also manipulate the system. Here in this case, in the bottom, we've generated a very specific sheared square lattice that we want to observe in it some interesting topological behavior. And these systems also, I think, have a very big potential for studying topological phenomena in metamaterials. Another class of systems that I recently started looking at is these networks of liquid diodes. So these are microchannels at the length scale of millimeters that, due to their asymmetric design, they can be unidirectional, behave like an electric diodes that allows electric current to flow only in one direction. And we're looking at all kinds of percolation phenomena when you build such a big disordered lattice of these diodes. We're also looking at active metamaterials or mechanical metamaterials, in which you have some external motors that measure the state of the system and respond to that. I won't get too much into this. I'll just finish with this movie showing a recent experiment that I was involved in which we looked at an array of pendula, just macroscopic masses of several hundred grams that are hung with strings of, 50 centimeters or so from the ceiling, and they just oscillate, but they're coupled to each other with these small knots up here. So this is my friend putting an initial condition of a Gaussian profile of oscillation within this array of pendula. These pendula are coupled to each other, so their oscillation, the oscillation of each one causes oscillation of its neighboring ones. And we demonstrated here what's called Bloch oscillations, which is something that's theoretically predicted to exist in any periodic system, in which this wave packet moves, as you can see here in the bottom left, in reciprocal space. So if you look at the Fourier transform of this image, if you look at the Fourier transform of this image, you can see the Gaussian in real space transformed to a Gaussian in K-space, and that the center of that Gaussian just shifts in momentum space or in reciprocal space till the end of what's called the Brillouin zone, and then it re-enters through the other end of the Brillouin zone, and eventually returns to where it started from. Again, I'm sorry the movie isn't playing very smoothly. It's also available on YouTube. You can watch it later. But the exciting thing, which okay, maybe now it will work. The exciting thing is that all this wave packet travels in real space and then returns to where you started. And at the end of this Bloch period, which has hundreds of oscillations of the individual pendula, you reach a spatial distribution which looks exactly like the initial condition, slightly decayed in amplitude, but you return to what you started from. And there are also interesting things here, topological, about comparing two experiments. So these are the behavior of the phase as a function of time in two different experiments that behave almost the same, but there's a very small difference between them, which accumulates to exactly a topological phase of pi between these two experiments that differ just by flipping all the interactions. So I think I'll stop here, and I would be very happy to take any further questions.